To welcome you to my lecture today. Of course, I want to welcome you to a new week. Um, I want to believe you've already seen assignment one and discussion on the canvas. Okay. Okay, so we're going to continue from probability. Today, of course, we're going to be focusing on further topics in probability. And of course, this is taken from chapter 2 of the textbook. Okay, now in the outline, I'm going to walk you through what we call probability axioms. Okay, so probability axioms, actually, they are rules that guide probability. Okay, I'm going to walk you through that. Then we also going to talk about conditional probability. Then we also going to start what we call the law of total probability and Bayes rule. Okay, so let's get started. If we want to talk about probability, of course, I believe you can all see this, right? Is there anyone who has any difficulties viewing that? You fine, right? Okay. Now, if we want to understand probability, we need to first understand possibility of events, which we call sample spaces. So I'm going to walk you through what do we mean by some fundamentals, as far as probability is concerned. We're gonna start with I think four of us start with experiment. Experiment is whatever we do that generates an outcome. Okay, where whatever we do, you don't need to be in a physics lab, you don't need to be in a chemistry lab. Now, when you we normally conduct experiments in this anywhere in the world, the life itself is an experiment. Like I said, anything you do that generate results, and you know what, the result could be favorable or unfavorable. Now, when we are now talking about the possible outcome in an experiment, then we're talking about sample space. And we're going to be using, um, you know, we're going to be using this. You see what I circle, right? Omega. That's a notation for sample space. Whenever you see that notation, okay, that represents sample space, which tell us the possible outcomes. Now, in a sample space, we got what we call events. We also have what we call outcome. So what is the difference between outcome and event? I'm going to say an outcome is a specific occurrence, or something I'm going to say a single result in an experiment. But when we talk about event is, it encompasses multiple outcomes. Does that make sense? So event is made up of multiple outcomes, while outcome itself is just a single result in an experiment. And I'm going to give you an example of an event. Event, of course, event is a subset of sample space. Don't forget, event is part of the occurrences in the sample space. Okay, now I want to demonstrate with an example. Okay, for instance, I want to conduct an experiment picking somebody in this class. Now, it's going to be an experiment because I know somebody will be picked. But before picking the person, I may not know who the person is going to be. Now, the random experiment is going to be picking a person at random. That's why it's called random experiment. Picking somebody at random, we're giving equal chance to everyone. Then the sample space is just going to be everyone in the class, because I want to choose from everyone in the class. I want to choose one person. Okay, the possibility now is going to be everyone in the class. Then maybe I have certain events in mind before choosing. And I was, okay, what is the event of choosing male? Okay, so we're taking a look at event A now. There's something I need you to pay attention to. You're actually going to, if you want to define event, you're going to use an uppercase letter. Okay. If you use a lowercase letter, you're going to lose point. Okay. Make sure you use an uppercase letter. Now, all males in class. It may be all females in class. That actually depends on what I want. Okay. And of course, event A occur if the outcome of the experiment is a member of set A. Now, each individual is actually going to be an outcome. Okay. But event is going to be, males. Of course, they're going to be more than one male in the class. And that was why I said, event is a combination of multiple outcomes. Okay. Now, and in the example, of course, the event A occur if the person we pick is a male. Otherwise, if the person we pick is not a male, then what would the person we pick is going to be the complement, okay, of what we have in mind. Is there any question on this? Okay, you are good, right? Okay. Now we want to go into probability. Let me tell you this. We can't talk about probability if there's no event. Event will come first. You see the way it is, right? The very first thing is experiment. After experiment, possibility. After possibility, within the possibility, event. Okay, and don't forget, events has multiple outcomes. Now, we now want to talk about probability axioms. Okay, we want to talk about axioms, the rules. We're talking about rules that actually guide our probability. And I'm going to start, I want to focus on two events, event A and B. Okay. I want to focus on event A and event B. Event A has some outcome in it. Event B also has some outcome in it. Now, what is the meaning of this guy here? Whenever you see this guy, that's an empty. Okay. An empty means there is no element in that particular event. And if there is no element in that particular event, the probability of emptiness is equal to 0. Does that make sense? The probability of emptiness equal to 0 because it's empty. There's no element in it. Okay. Now, another thing I want to talk about, if I'm talking about event A now, okay, what is the probability associated with event A? Of course, the probability associated with event A is going to lie between 0 and 1. Okay, 0 and 1 are the extreme values of probability. The 0 indicates uncertainty, 1 indicates certainty, and between 0 and 1, of course, is what is realistic. Does that make sense? Okay, so the P of A actually indicates probability of an event A occurring. Now, I want to go to the complement now. Now, mathematically speaking, if I'm interested in event A, okay, if I'm interested in event A, then other event that I'm not interested in become what I call the complement of A. So mathematically speaking, because the probability of event A plus the probability of the complement is equal to 1, and why we're able to get that is because event A and its complement are mutually exclusive. When event are mutually exclusive, it means they constitute the sample space. Then it means the probability, when I add them up, okay, they're actually going to give us the probability of the sample space. The probability of the sample space is always 1 because sample space is a sure event. I'm going to say that again. Sample space is a sure event. Now, because of that, if I want to obtain the probability of not A, then it's going to be 1 minus probability of A. Does that make sense? Any question? Now, I want to move to two events right now, and we want to prove this guy. Okay, this, I showed you this guy last week. This is not mutually. Okay, we're having two events where A can occur separately, B can occur separately, and A and B can also occur together. I'm going to give you an example here, like maybe Event A is I order food from restaurant A, and event B, I order another food from restaurant B, and I want to know what is the probability, okay? I want to know what is the probability of whether they will come, the two order will come on time. It's either the food that I order from restaurant A come on time, or B come on time, or they both come on time. Does that make sense? So that's going to be an example of non-mutually. But what I want to do now, I'm actually going to prove this. I'm going to show you how we want to prove this guy now. Okay. Now I'm going to use what I call the Venn diagram, and I need you to take a look at the Venn diagram. Okay. I'm going to draw this guy. You see that? Then this is A, this is B. Okay. Now here is A intersection B complement. Okay. That's the side. And this guy is A complement intersection B. You know, this is like A only. Okay, there's no B. This is B only, there's no A. But what about it in the middle? The middle is going to be A intersection B. Any question about how I interpret that? Now, if I want to focus on A, if I want to focus on probability of A, okay, it means I'm going to add this guy to this guy. Okay, so I'm actually going to do the probability of A intersection B, okay, plus the probability of A intersection B. I can call that guy equation 1. Okay, I'm focusing on A, total A. This is A only, but this is the total A. Okay, now I also want to do the same for probability of B. So which is going to be the probability of A complement plus the probability, and I'm going to call that equation 2. Okay, the probability of A equal to that, probability of B equal to that, call that equation 1 and equation 2. Now the next thing, what am I looking for? I actually want to get the probability of A union B. Okay, now if I want to get A union B, I'm going to add all of this, right? A union B. I'm going to add all of this if I'm looking for probability of A union B. Now, in the probability, I'm going to let me clean this guy. Now, in the probability of A union B, like I said, okay, probability of A union B is going to be the probability of A complement intersection B plus the probability of A intersection B complement plus the probability of A intersection B. I'm going to call that equation 3. You know, if you take a look at what I draw the other time, you know, if I want to get probability of A union B, I'm actually going to add all of them. Any question? I'm going to add all of them. Now, if I had all of them, I have equation 3. Now, what I'm going to do now, from equation 1 and 2, from equation 1 and 2, I'm actually going to solve for the probability of A complement intersection B. And now, if you take a look at, do you know that from 1, I can have the probability of A intersection B complement to be equal to probability of A minus probability of A intersection B. Do you see that? Okay, from here, I can do this guy is going to be this minus that, which is what I have now, right? Okay, so I'm going to clean this guy up now. Okay, now maybe I call this guy equation 4. Then I'm going to do the same thing from equation 2. From this equation, I also want to make this guy the subject of the formula. So making that guy the subject of the formula, the probability of A complement intersection B will be equal to probability of B minus the probability of A intersection B So which is going to be 5. You're going to call that equation 5. Then I'm going to clean equation 2 up. Now, you know what I'm going to do now? I'm going to plug in equation 4 and equation 5 into equation 3. Now, you see this guy? You know, it's right here, right? I'm going to put the whole of this. You see, this guy is equal to this. I'm going to put the whole of that into that. So when you do that, okay, when you simplify, when you do that, it's actually going to give you a probability of A union B, which is going to be probability of A plus probability of B minus probability of A intersection B. So when you do that, this is what you're going to get. That is how we derive it. Any question? So like I said, you plug in equation 4 and 5 into equation 3 and you simplify. This is going to be your final expression. And this is how we derive the probability of the union between A and B situation where event A and B are non-mutually exclusive. Any question? Okay, now in the absence of question, I'm actually going to move. Okay, now that can also be extended to 3 events. Okay, that can be extended to 3 events. But you know what? I'll quickly walk you through how to derive that of 3 events. Like in this class, this is 3021 honor. We're actually gonna go more mathematical. Okay, this is different from the conventional 3021. Now, what I want to do now, I want to prove that probability of A union B union C equal to all of that. Okay, that's going to be super easy. You're going to see how that's going to play out. Now, if you want to do that, okay, we're first going to start with what is the probability this is what we want to derive, right? We want to derive this guy. What we're going to do is take a look at this guy. We can let D be A union B. Okay, what am I going to write next? It's going to be P D union C. Any question? Or now, now D, now replace A union B. I want to simplify that. Now, if you take a look at this guy, of course, based on what we've derived about non-mutually, this guy is going to be equal to what? Probability of D plus probability of C minus probability of D intersection C. Based on what we just derived for 2 events that are non-mutually, we have this. Any question up to this moment? Okay, so what we're going to do now is I'm going to return wherever I see D now, I'm going to put A union B. That's what I'm going to do next. You following it? Okay. If you don't get it, please let me know. Okay, so far so good, right? Okay. Now, I want to clean, wherever I see D now, I want to put A union B. Okay, I want to write that. So I'm going to write the probability, okay, the probability A union B union C equal, instead of probability of D, I'm actually going to write the probability of A union B because, A union B, D represent A union B, okay, plus the probability of C minus the probability. I want to plug in inside D, A union B, okay? So A union B intersection C. Don't forget the A union B you are introducing, that is D, you can put a parenthesis on that. Any question? Any question? Super easy, right? Okay, now then let me close this guy here, okay, so that now the next thing I'm going to do now, okay, it's super easy now, okay, it's super cool. Okay, so the next thing I'm actually so the next thing I'm going to do is take a look at this. The probability of A union B, of course, we can split it as, using non-mutually approach. So this is going to be equal to the probability of A, I'm talking about this guy here, plus probability of B minus probability of B of A intersection B. Give me 1 second. Okay. So the probability of A intersection B. So what have this guy is the same thing as this guy, then plus the probability of C, right? Now, right here, I'm going to apply a rule. Okay, it's like something here we go with this and this, and something here we go with that and that, and the union is going to be inside them. So, so that is going to be, I got a minus into, okay, the probability into A, probability into A intersection C, okay, then don't forget the union in the middle. Okay, so here now, union, okay, union B intersection C, B intersection C. Take a look at that. Okay, this guy now, we can write that as A intersection C, union B intersection C, which is what I've written here. Take a look at that. Okay, now the next thing we're going to do now is to simplify this guy. Okay, don't forget, if I have something, union something, I can rewrite it as non-mutually, right? I can rewrite it as probability of this guy plus probability of this guy, then minus or the interception. Does that make sense? I'm going to say that again. There's a union here, right? This is an entity. This is another entity. I can say probability of this guy plus probability of this guy minus all of them, like combining this and this. Okay. Now, if I do that, in that situation, this is going to be, so when let me see. So it's going to be minus, let me write it here. It's going to be minus into probability of A intersection C plus probability of B intersection C minus probability of A intersection B intersection C. Okay, now I'm talking about this guy here. Okay, this guy here is going to be this, this, and this. And don't forget, there's a minus here, right? So there's going to be minus of this, and what? Plus of that. So by the time you put that together, it's going to give you that expression. Any question? That is how we do that of the union of three events. Any question on that? You can try that, okay? Now, so that is how that is done. Give me 1 second. Okay, now, then for mutually, it's just adding that. Of course, we did that the other time, okay? For mutually for two events, okay? Now, I want to move right now. I want to move into conditional probability, okay? I want to move into conditional probability. Now, whenever you see this notation, okay, that means, give me 1 second. Whenever you see this, it means the probability of A given B. That's a conditional sign. What that means is for A to occur, B must have occurred. That's what it means. Now, the formula is just going to be the ratio of the probability of the joint to the probability of B. Okay, so that is a formula for conditional probability. Okay, and if you remember what we did the other time, if you want to start from here, it means this guy multiplied by that guy, which is the dependent that we did on Friday. You remember on Friday, we apply multiplication rule in two ways, one for independent and one for dependent. If I want to go from here, it's going to be this multiplied by that. This is for the dependent, if you remember. So, I can also find the conditional probability. So the formula for conditional probability is that, and of course, automatically confirm the multiplication rule. Like I said, if I want to start from here, so it's going to be this multiplied by that. And let me tell you this. This is the same thing as this. Why? Because A intersection B is the same thing as B intersection A. I don't know whether you've heard about commutativity. Where they commutate, there's a commutative law. So B intersection A is the same as A intersection B. Okay? Now, having used that, before I'm going to go into partitions, before I'm going to go into this, I want to first explain the special case of partition. And I need you to pay attention now, because right now we are now, getting into rigorous notation. And what I'm going to do, I'm going to explain what is behind the scene, what is behind this notation. Now, I need you to take a look at this. This is a sample space, right? A sample space is partitioned into B and B complement. Maybe in this class, B is events of those who like sports. And this guy, those who do not like sports. So B and B complement constitute the sample space. Does that make sense? Okay, now if I partition sample space into this and this, I need you to take a look at this guy here. Give me 1 second. Take a look at this guy here. Do you remember when I draw a Venn diagram the other time? A, the total A. Okay. Let me draw it here so that you can see. I'm talking about if this is A and this is B, okay, and this is A intersection B, okay, and this is actually A intersection B complement, okay. Now what is A? A is this plus this, right? Which is what you see here. So if I'm focusing on event A, and that very event A may be somebody, maybe event A is a event of somebody passing this course. Somebody can pass this course and love sports, or somebody can pass this course and do not like sports. Does that make sense? I understand all this because I relate. Don't just look at notations. If I were you, just take a look at how you can relate that to real life. Look at what I just said. I want to know the probability of somebody passing my course in this class. And B is the event that some of those who like sports, and B complement those who do not like sports. And if I want to calculate the probability of somebody passing my course, it's actually going to be somebody can like, you can like sports and pass my course, okay? And you do not like sports and you pass my course. This is a total probability now, okay? Now, but if you take a look at the situation here, I only partition the sample space into two events, liking sports or not, where the interest is on calculating another event, okay? Now, if you take a look at this guy now, I want to apply multiplication rule for dependence. Is that not a suggestion? Based on what we did last week, then for this guy, they want to have a bar, it's going to be that guy. Do you see that now? Now, I now want to generalize, okay? So instead of partition into two, I want to partition into many. That is going to be this guy here, where I'm no longer talking about B and B complement, but I'm talking about B1, B2, B3, B4, where I partition the sample space into how many? Into B1 up to BM. Any question? Maybe what I'm going to be talking about may not be maybe different kind of sports, football, soccer, what should I want, baseball, and so on like that. Maybe that's what I'm talking about. And I want to find the probability of somebody passing my course. Somebody can pass my course and that person may like soccer. Somebody can pass my course, that person may like baseball. So and so on like that. Now, do you now see that this guy here is a generalization of this? And two of them are talking about total probability. Any question about this? Any question? You're good, right? Okay, now I want to move to now. Let me tell you the implication of total probability is the Bayes rule. Because you know why? Uh, the Bayes theorem, okay, is the denominator for Bayes theorem is the total probability. This is P of A, right? What was the P of A? What was the P of A? The P of A, give me 1 second. The P of A was actually total probability. So, because I'm going to Bayes theorem as put forward by Reverend Thomas Bayes 1749. So, what I'm going to do is I actually going to use this as a kind of as a denominator. So when you take a look at this guy now, give me 1 second, you're gonna see. Okay, now we take a look at this guy now. By Bayes theorem, the probability of B given A is different from probability of A given B. But let me tell you this. If I write probability of B given A, what do I normally write here? Probability of A intersection B divided by that. The probability of A intersection B can be written like this if you follow dependent rule in multiplication, right? Is this guy, right? Now, if I have this guy, what is probability of A? It's a total probability, which is this guy. Total probability that I just show you. Now, the question now is, what is the difference between this guy and this guy? What is the difference between probability of BJ given A and probability of A given BJ? Now, the probability of BJ given A is what we call posterior. That's a posterior probability. Okay, this guy is a likelihood, and this guy is a prior. Now, what Reverend Thomas Bayes was trying to do is, let's say, for instance, somebody was accused of wrongdoing. I want to apply this in the court of law now. Okay, this guy is what is the probability that the person is guilty given evidence? Is different from, okay, what is the probability of the evidence given the guy is guilty? The two of them are not the same. Another way I'm going to put this is if I don't want to move, if I want to move out of court of law, I want to go to disease. Okay, somebody can. What of if somebody tests positive? What is the probability that disease is present? Is different from, somebody. This is a machine, and somebody has tested positive. What is the probability that disease is present? Because why do we need to doubt? We're in a stochastic world. The efficiency of the equipment is not 100%. That's what I mean. So if the machine say so, if the machine say that this guy has a disease, I mean, what is the probability that disease is present? That is different from a situation whereby this guy has the disease. We know he has the disease. What is the probability that the machine is going to say so? Say yes. The two of them are not the same. I'm going to say that again. The first one is trying to say, if the machine actually says somebody has a disease, what is the probability that the person duly has the disease? Is different from, we know somebody that this guy has a disease. Okay. What is the probability that our machine will detect that? So the two of them are not the same. Okay. So I'm going to walk you through all of that. I'm just trying to show you, so this is the posterior And this is the prior. The prior is unconditional probability. If you take a look at probability of B is not conditioned on any event. We call that unconditional. That's a prior. What do we mean by prior? The prior probability is the probability of the state of nature before you collect data at all. Before collection of data, what is the state of nature? It's just like before evidence, what do I have in mind? Okay, about somebody. I accuse somebody of stealing. Okay, I take the person to court. That's still going to be prior. Okay, then this is a likelihood. The likelihood is not going to be the evidence. Then the posterior is updating our prior knowledge with the evidence available, with the new information. Does that make sense to you now? So according to Reverend Thomas Bayes, what he was trying to do is we could improve on the way we take decision if we can combine our prior knowledge with the likelihood. The likelihood is the evidence. Does that make sense? But at time before the evidence, you can accuse somebody, and that's why in the court of law, an accused is innocent or until he's proven guilty by law. Does that make sense? Okay, now I want to go into chain of event. Take a look at this guy now. Chains of event. We have event A1, A2 up to AN. So many events this time around. And we want to find the probability of the joint occurrence of all of them. You remember the one we did last week. We only focus on two events. When two events are independent, what happens? The probability of when they are independent, when we normally have this. Okay? When they are independent. What of if they depends? If they depends, it's going to be this guy. Does that make sense? We got two forms of multiplication rule. One for independent, the other one for dependent. Now, this is for two events. Now, we want to generalize it to so many events. I want, A1, I want to find the probability of the joint occurrence of A1 up to AN in such a way that they depend. You know what is going to happen? If I have a probability of A1, the second one will be probability of A2 giving A1 as occur. The next one is going to be probability of A3 giving A2 and A1 as already occur, and it's going to go that way. Therefore, this is a generalization of dependent events. This is the multiplication rule for dependent events in, when we are focusing beyond two events. Does that make sense? That's what I mean here. Okay, we still want to continue on the axioms. If I'm not able to finish this material, that's where we're going to start on Wednesday. But this is critical, but I just want to make sure you really understand it. And this is being recorded, okay? So this is being recorded. Okay, now we want to talk about, we want to revisit the multiplication rule for two events for dependence, right? If I'm talking about A intersection B, but if I'm talking about B intersection A, it's going to be this guy. Here I mentioned A first. That was why you see probability of, that's why you see this. And here I mentioned B first. That was why, but because this guy and this guy are commutative, then they're going to be equal. Does that make sense? They're actually going to be equal. Now, I want to take you to something else. I need you to take a look at this. That's for non-mutually, right? That's for non-mutually, right? Okay. Do you know that from there we can also, if they are conditioning, all of them can both condition on A. They can both condition on the same letter. B union C condition on A. B condition on the same A. This condition on A. This condition on A. Take a look at that. So, but it has to be the same. thing is the same event they are conditioning on. Does that make sense? Okay, I want to appreciate those who send who try the extra credit. I want to say you all have 1 point. Those who send you know the the proof of the solution to the exercise that I gave the other time. Those of you that send it in, you all have 1 point. Now take a look at this. I want you to use the knowledge here, right? And tell me which one is going to be this. There's going to be another extra credit. I like awarding extra credit. Don't forget here, this is this guy here. We wanted to simplify and tell us which one is equal to. So you can if when you attempt that, you can send me, that will be another extra credit. Okay, I want to move. I want to move right now to something else. I need you to pay attention to this guy here. You know, if I have probability of, take a look at this. If I have probability of B complement, that will be 1 minus probability of B, right? Do you know I can introduce something they can be both conditioned on the same event? That's correct. Do you see that? If you want to follow up with this, we can condition them on the same event, which is going to be event what? A. Hey. Okay. So if this is B complement, this is going to be B, and they both put a condition on that. Okay. So I needed to take note of that. So that is possible. Okay. So that is what I just showed now. Okay. From here, I can just, make them to condition. But take a look at this. This is not going to be right. Okay. If you prove this guy out, it's not going to be this. And the only condition where that is going to happen is when P of B equal to 1. If P of B equal to 1, because which is what we have here. Does that make sense? Okay. Now, of course, I'll show you this one today using the Venn diagram. Okay. This is like B only. B only is going to be A minus the point of intersection. Okay. Okay. Now, they ask you this question here, true or false? Of course, it's going to be false. You know why? When you have an event here, the complement should be here. And if they want to condition on something, they should condition on the same thing. But this is A complement. This is false. That's not true. So whenever there is an event here, that should be complement here, or complement here, the event here, but what they condition on has to be the same. And that was why I said, this is the diagrammatical representation of that. Okay. B, there is a B within A. There's another B within A complement, and all of that is the sample space. And I said, knowing B within A, which is here, tell us nothing. It does not tell us this. Tell us nothing about what B is doing with the A complement. So this is not true. Okay. Now, we can also show this guy here. The probability of B given A that is equal to this. Okay. Because of my time, you can also try this. Okay. If you don't get it out, I'm going to walk you through that. I want to make sure I get to like 2 more slides before I go. Now, when we are talking about partition theorem under the law of total probability, situation where events are disjoint. Disjoint means they have nothing in common. If they have nothing in common, A intersection B will be empty. You can see them. They are not connected. Then they are actually mutually exclusive. That's why this guy is going to be probability of A plus that. You see that? And for all, it's going to be this. But situation where this event is empty, what is the probability of emptiness? That will be 0. When I plug in 0 here, then I'm trying to say they are mutually exclusive. This is for 2 events. What about for 3 events or for multiple events, B1, B2 up to BK, in such a way that there's no connection? Then we're going to say BI intercept BJ will be empty. Could be B1, could be B1, intercept B2, or B2, intercept B3, because all the B1 up to BJ, they are mutually exclusive. Now, if that happens, then if I want to write them, this is a way to write them in short form. You know the meaning of this guy? B1 union B2 union B3 union up till I get to BK. That's the shortest way to write it. Does that make sense? Okay, which is this guy here. This is the shortest way to write it. And they all constitute what? Sample space. This is like state in the United States, Minnesota, Illinois, Pennsylvania, and so on like that. All states in the United States are mutually exclusive in a way. Okay, and they all constitute United States. This is a sample space. Okay, and there is no any overlapping, and that's why they are all disjoint. Does that make sense? That's why they are all disjoint. Okay, now situation where I have the sample space partition maybe into 4, B1 up to B4, but I'm interested in A, even A in each of them. That's why you see A intercept B1, A intercept B2, and so on like that. Then that will be total probability, which is I want to find probability of A, which could be probability of adding this to this to that to that. That's why you have this guy. This is more or less like the total probability that we talked about the other time if we are only partitioning the sample space into 4. And that will take us to Bayes' theorem, okay, which is a Bayes' theorem that I've already mentioned. Okay, I think I'm going to stop. Now, this is a general case of Bayes' theorem. This is a situation where the partition, I have M partitions, M, like the sample space is partitioned into M. I can have a special case of that where it's only partitioned into 2, B and B complement. Do you see that? And by the time I'm going to start next time, I'm going to start from application to disease. Okay, how can we use Bayes' theorem to solve a problem that has to do with this? This is where I'm going to start next time. Any question today? Any question? Okay, so like I said, I'm going to publish my recordings again today. Make sure you check my YouTube channel in case you want to catch. Like I said, all my lectures are being recorded. And of course, my office hour is every Tuesday, 10 to 12. If my office hour is conflicting, please reach out. I'm flexible. Okay? Make sure you all stay safe and have a lovely day. Bye for now, everyone. You're welcome.
Summation of all this on the bottom.
Yeah.
Is this from I?
I start from 1 to M. So
Oh,
this is
okay.
like
So this is different from J.
It's different from J.
So J is not incrementing.
Exactly.
Okay.
Exactly. You're right.
Okay.
Mm-hmm.